Determining the correct conductor size for motor branch circuits is essential for electrical safety and performance. National Electrical Code Table 310.16 provides ampacity ratings for conductors based on their insulation temperature rating. The question often arises whether to use the 60 degrees Celsius, 75 degrees Celsius, or 90 degrees Celsius column when sizing conductors for a motor. Generally, for most modern electrical equipment and new motors, it's safe to use the 75 degrees Celsius column of Table 310.16. This is primarily because modern electrical equipment is designed to operate at higher temperatures than older equipment. Furthermore, new motors typically incorporate insulation materials rated for higher temperatures, allowing them to handle greater heat without degradation. However, there are specific situations where using the 60 degrees Celsius column might be necessary. These are primarily dependent on the temperature ratings of the terminals and the ambient temperature. Let's delve into the details. Firstly, the temperature rating of the terminals is crucial. Electrical equipment, such as circuit breakers, disconnects, and motor starters, have terminals with specific temperature ratings. These ratings indicate the maximum temperature the terminals can withstand without compromising their performance or safety. The conductor's ampacity, as determined by the temperature column in Table 310.16, must be suitable for the temperature rating of the weakest link in a circuit, which is often the terminal. For instance, if the terminals are only rated for 60 degrees Celsius, you must use the 60 degrees Celsius column for conductor sizing, regardless of the motor's insulation rating. Secondly, ambient temperature plays a significant role. If the motor operates in a high ambient temperature environment, the conductor's ability to dissipate heat is reduced. High ambient temperatures can raise the conductor's operating temperature, potentially exceeding its insulation rating. In such cases, using the 60 degrees Celsius column or applying ampacity correction factors is necessary to ensure the conductor operates within its safe temperature limits. Thirdly, consider the motor's load. If the motor is expected to be heavily loaded, it will draw more current, generating more heat in the conductors. This increased heat can necessitate using the 60 degrees Celsius column or applying ampacity correction factors to prevent overheating. Now, let's consider a specific example involving a 3-phase 208 volts, 7.5 horsepower motor. To determine the appropriate conductor size, follow these steps. 1. Determine the motor's full load amps or FLA. According to NEC Table 430.250, a 7.5 horsepower, 208 volts, 3-phase motor has an FLA of 24.2 amps. 2. Apply the 125% factor as required by NEC 430.22. This section mandates that branch circuit conductors supplying a single motor must have an ampacity of not less than 125% of the motor's full load current. So, 24.2 amps times 1.25 equals 30.25 amps. 3. Select the conductor size based on the calculated ampacity. Using the 75 degrees Celsius column of Table 310.16, we find that a number 10 copper conductor has an ampacity of 30 amps. However, because our calculated ampacity is 30.25 amps, which slightly exceeds the number 10 copper conductor's rating, we might consider using a larger conductor. 4. Check the terminal temperature ratings. Before finalizing the conductor size, it's crucial to verify the temperature ratings of the terminals on the motor, starter, and any other connected equipment. If the terminals are rated for at least 75 degrees Celsius, a number 10 copper conductor is suitable. However, if the terminals are rated for only 60 degrees Celsius, you must use the 60 degrees Celsius column of Table 310.16. In this case, a number 10 copper conductor would not be sufficient, as its ampacity in the 60 degrees Celsius column is lower than 30.25 amps. You would need to select a larger conductor size that meets or exceeds the required ampacity at 60 degrees Celsius. 5. Apply any necessary correction or adjustment factors. If the ambient temperature is higher than 30 degrees Celsius, or if there are more than 3 current-carrying conductors in a raceway, you must apply correction or adjustment factors as specified in Table 310.15. These factors reduce the conductor's allowable ampacity, potentially requiring a larger conductor size. For example, if the ambient temperature is 40 degrees Celsius, you would need to apply a correction factor of 0.88 to the conductor's ampacity. This means that the number 10 copper conductor with an ampacity of 30 amps at 75 degrees Celsius would have a derated ampacity of 26.4 amps. In this case, you would need to select a larger conductor size to meet the required ampacity of 30.25 amps. 6. Consider voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can negatively affect the motor's performance, causing it to run hotter, slower, and less efficiently. NEC 210.19 FPN number 4 and 215.2 FPN number 2 recommends that voltage drop on branch circuit should not exceed 3% and voltage drop on feeder should not exceed 5%. To calculate voltage drop, you can use various online calculators or consult engineering tables. If the calculated voltage drop exceeds the recommended limits, you may need to increase the conductor size to reduce the impedance and minimize voltage drop. 7. Select the appropriate overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overload and short circuits. The size of the overcurrent protection device must be coordinated with the conductor's ampacity. NEC 430.52 provides guidelines for selecting the appropriate overcurrent protection device for motor circuits. In general, the overcurrent protection device should not exceed the conductor's ampacity, unless specifically permitted by the code. 8. Choose the correct wiring method. The wiring method refers to the type of raceway or cable used to enclose and protect the conductors. Common wiring methods include conduit cable trays and direct burial cables. The choice of wiring method depends on various factors such as the environment, the type of building, and the applicable codes and standards. The wiring method must be suitable for the conductor's insulation type and the operating conditions. 9. Ensure proper grounding. Grounding is essential for electrical safety. It provides a low impedance path for fault currents to return to the source, tripping the overcurrent protection device and energizing the circuit. NEC 250 provides detailed requirements for grounding electrical systems and equipment. The grounding conductor must be sized appropriately to handle the available fault current. 10. Follow all applicable codes and standards. Electrical installations must comply with all applicable codes and standards, including the NEC local building codes and any other relevant regulations. These codes and standards are designed to ensure electrical safety and prevent electrical hazards. It's crucial to consult with a qualified electrician or engineer to ensure that the electrical installation meets all applicable requirements. In the specific case of a new motor that isn't expected to be heavily loaded and assuming the terminals are rated for 75 degrees Celsius, using the 75 degrees Celsius column of Table 310.16 to determine branch circuit conductor size is generally safe. Therefore, a number 10 copper conductor would be suitable, provided that all other factors such as ambient temperature, voltage drop, and overcurrent protection are also considered. It's always a good practice to err on the side of caution and consult with a qualified electrician or engineer to ensure that the electrical installation meets all applicable codes and standards and is safe and reliable. Remember, the NEC is a comprehensive document, and it's essential to consult the specific sections relevant to motor circuits for detailed requirements. Understanding these principles ensures electrical installations are safe, compliant, and optimized for performance. Always prioritize safety and consult with qualified professionals when working with electrical systems.